Welcome to Pipeline Conversations, a machine learning podcast by ZenML. This week, I spoke with Mateo Rojas-Carulla, the CTO and a co-founder of Lakera and Matthias Kraft, also a co-founder and the CPO there. Lakera is an AI safety company that does a lot of work in the computer vision domain, building a platform and tools for users to gain more confidence in the output and functionality of their models. We discuss how they think about the testing of machine learning models and about how having this safety element up front has implications for how you go about the testing and ensuring robustness. We specifically dive into how to go about testing computer vision models and the various pitfalls that are to be found in that domain. Everything mentioned in the show will be listed in show notes as usual, and without further ado, here's the conversation.
Thanks a lot, Alex, for having us on. My name is Mateo. I'm a co-founder and CTO of Lakera, a startup based in Switzerland. And these days, I'm quite obsessed about the questions of or around, rethinking how we build machine learning systems, and specifically machine learning systems and computer vision systems that we can trust. There are massive challenges ahead in this direction, and I believe there are pretty fundamental contributions we can do at this time. My background is in computer vision and applied math, which I did in France. And after a very short, very short passage through the finance industry, I joined the PhD program in machine learning. It was supervised by Bernard Trelkoff in the MPI and Rich Turner in Cambridge. And my main focus there was really around transfer learning and really thinking, how do machine learning systems generalize? And more fundamentally, what kind of assumptions can we make around probability distributions, the ones used for training, for testing, and ultimately the real world, in a way that you can even talk about generalization in that context. And at the end of the PhD, I was really still very fascinated by the field, but I felt like I had been living a little bit in a researcher's cloud, doing my little projects and my little papers. And I wanted to see a little bit more how things are built in the real world. And at that time, I decided to join Google here in Zurich, and actually to detach myself from the machine learning world and go to more traditional software engineering. And that was a really fascinating experience. And I was working in Google Search, and it was very interesting to go from those PhD projects to building planetary level systems, that really evolve at very rapid speed. And for me, the major kind of culture shock that happened there was to see how traditional software systems are built in a way that you can actually deploy at that scale and actually know that things will work and that they do work. And it felt like just a massive gap from how we develop machine learning systems today. And I believe we'll get an opportunity to discuss that going forward. But on that note, maybe Matthias can go ahead.
Yes, gladly. I'm also a co-founder at Lakera and the CPO, which means I am sort of Mateo's counterpart in many ways. And in a practical sense, it means that I spend a lot of time trying to understand the problems development teams face every day in developing computer vision systems, and kind of trying to mold solutions on a product level around the problems that they have. Whereas then I can hand them over to Mateo to actually build the solution, since he's in charge of the technical bits. And yeah, to give a bit of context, before starting Lakera, I was actually also working as a computer vision developer. In particular, I worked on building essentially camera-based equivalents of GPS systems. So given an image, how can you find out where you are in the world? And there I got to play with a lot of computer vision technologies, from very classical stuff like SLAM and global localization to more ML-based approaches. And what it really meant is that a lot of the challenges that we're now trying to solve, I actually also experienced in the past, which is, I think, a good starting point to do this. And yeah, even going back further than that, I have a background in physics, and I also stayed on to do a PhD like Matteo, but in theoretical physics, so very unrelated to anything I do now. But I think it taught me a lot on how to approach problems and tough challenges, which is very, very fun. And my main sort of motivation at work, solving large challenges, and that's also what we try to do with Lakera.
As a way of situating what it is that Lakera does, maybe you could talk a little bit about the core problems that you deal with, or the core problems that your users deal with on a day-to-day basis. Like, what is broken about this system?
Yeah, I mean, at the starting at the 10,000 feet level, what we're trying to tackle is really the challenge of AI safety in many ways. Like, how can you build AI systems, and in particular, we focus on computer vision that are safe and work as expected when you deploy them in the real world. And what can development teams do to ensure the safety of those systems? And very concretely, I think some of the challenges I always faced were around answering questions like, where does my system actually work? Right? It's not a trivial question to answer. Previously, when looking at more traditional software approaches, it'd be relatively straightforward in some sense to really answer, okay, does my computer vision system work in this particular situation or not? But with more complex systems, and in particular with computer vision, where you learn most of the behavior, questions like, okay, now you build a stop sign detector and it works, but does it still work if the color of the stop sign changes? They become very non-trivial to answer. And those are the kind of questions that if you deploy computer vision in industries where there's a little bit of a security aspect to them, and important things are at stake, those are the questions you really have to answer. And that's kind of what we try to answer with the products we built at Lakera.
So maybe you could give a kind of a concrete example, just to tie it down to a specific use case. How does safety and being able to trust what your ML model is doing, like how does this specifically differ for computer vision, since this is kind of the focus of what you're doing?
So I think one pretty fundamental. I think maybe we can actually take it a little bit back and try to understand why the issue of safety is particularly challenging for AI systems, and more precisely for computer vision systems, maybe. And I think as part of that, kind of good examples should emerge. And maybe one fundamental aspect is that, as I mentioned, going back to my experience becoming a software engineer in a more traditional setting, the way we test traditional computer vision systems, traditional software systems, is essentially by writing components of code that have a very clear contract. And this contract, is implemented by a human, right? We know exactly what we want this function to do. We know in which settings it should work. And now we are writing tests and trying to understand very well how this component behaves. And in a way, the complexity of the software really is a bit of an emergent behavior of all of these small pieces of code that are interacting together, each of those very well understood. And in some sense, the kind of macro behavior of this software becomes arbitrarily complex, but really as often as an aggregation of very clearly understood components. And specifically, I think the kind of safety or test, ability to build such systems safely, in part results from the fact that we can test all of these components extremely well in isolation, and as a result, the kind of testing quality that comes out becomes relatively high and trustworthy. Now, with the machine learning and computer vision, I think that is fundamentally flipped. So, the way that we can think about it is you have a data set, you have some data that you can collect in the world, and you have a model class that is arbitrarily can approximate arbitrarily complex functions, and is extremely powerful. And now we have also the computational means to actually train that and to actually extract the signals and the dependencies that are in that data set that allow us to solve the problem. And now, and this may seem a little bit simplistic in some sense, but ultimately we write a few lines that say, load data, train model, model.fit, and at the end we're going to have a lot of complexity, and this complexity was not an emergent behavior of a bunch of different components like in traditional software, but is now just a system that is in front of us and is extremely complex and difficult to understand. And I think that's fundamentally where I see one of the key difficulties in ensuring the safety of AI systems as opposed to traditional systems, as where we have a lot more knowledge, is that we now have to understand whether they work as we obtain them, and the issue of understanding how they actually perform is pretty challenging, and we can get into details of why that is. But I think very concretely, if you want something like an example, we can imagine building something like a medical device, where you may want to predict some medical condition, maybe, given some X-rays, you want to predict the presence of some disease, and now you're going to download some data sets online. You're going to maybe even work together with some hospital. You're going to train a model based on a state-of-the-art network. It's going to look great. After a few iterations, on your very nicely left out validation set, you get like amazing numbers. You think you have your billion-dollar company ready, and then you go for a little pilot in the clinic next door, and then you realize that everything breaks. And I think that is essentially something that happens at scale in machine learning. We have a certain knowledge of what it means to test a machine learning system, which essentially relates to aggregate metrics and to held out data. But then what it actually means to work in production and to work safely in production needs significantly more work. And development teams ultimately have the burden of proof, to show that it works, but the knowledge is missing. And I think precisely that kind of questions, like how do I know that I'm ready to go to a clinical trial? How do I know that I'm ready to go for production? How do I know that my system is actually work as intended in once it hits production? These are very concrete the questions we want to help people answer. And I think, I gave the medical example, but this goes way beyond that. You can imagine, autonomous driving, autonomous inspection, industrial inspection, all sorts of applications in healthcare. All of these things have this fundamental challenge of ensuring that things actually work and that you build the system you wanted to build. And that's where we as Lakera come in and try to contribute and help.
I'm kind of curious, like if you have any sense of how you think we ended up where we are, because as an outsider, I guess, if you told them, well, yeah, we can do these amazing things with computer vision technology and whatever large models that we have, but when it comes down to it for serious systems, we can't really tell you whether, like, we can't really trust them properly, and we don't maybe understand this. Like, does this tell us something about the immaturity of the field or the priorities of how people have gone about building these systems in the past? What's going on there?
Yeah, I would. I can give one part of the answer, which I think it's partially because we look at problems which are just much harder than the classes of problems that we looked at before. So, me having worked on classical computer vision as well as ML systems, I kind of know how difficult it is to build a classical CV system with, geometrical methods, thinking about all the cases and really trying to grapple with the problem. And there's an inherent limitation in that approach because the world is much more complex than I at least have the ability to handle in terms of solution approaches that I come up with. Whereas machine learning gives this, fantastically powerful method to do things that I cannot do by hard coding them or by doing some fancy maths. But of course, there's a downside to that, which is that I know a lot less about the system that I'm actually building and how it works. And I think that's a lot of that comes down to being a symptom of actually solving a much harder problem than we tried to solve before. But there is also the side of maybe data science, being maybe not quite a mature engineering discipline as compared to software engineering. So there's that aspect too.
So I think that's indeed a good point as well, because I think it's very easy to forget how young machine learning as a really prominent discipline is. I even for me, I started my PhD in 2014, and at the time I was implementing gradients by hand, debugging with finite differences and things that today are just unthinkable. And it is a while ago, but it's not that long ago. And I think the field has progressed significantly, but more in a very constrained setting, right? Where we have become really good at solving very punctual problems, where we know we have the data roughly, we know we're testing on similar things, and the effort has gone in some sense in both a methodological and more engineering level work to like scale these models in a way that you can get to arbitrarily impressive applications. I mean, lately, GPT-3, all these different systems are really quite impressive. But I think that has a little bit come at the cost of not investing enough in the kind of know-how and work and research around how to actually deploy these systems in a way that they work. I think what the effort has really been in learning more and more complex representations in some sense, and more complex problems. And in some sense, if you think about it, one could say these systems just make bigger and bigger failures as well. GPT-3 does amazing things, but you can also make it fail pretty gloriously. And I think what's happening now is that we have invested a lot in this, and it has been a bit of a sprint in some sense. We're talking like a 10-year development, and now the core technology is at a point where it's actually starting to be used more and more for industrial applications. And there we are actually realizing that, it's just not enough to learn complex mappings and complex dependencies and so on. But we actually need to have a responsibility as providers, of customer facing applications to guarantee quality and safety. And I think we're just kind of at the process where the corresponding research and so on is starting to be looked at, and we're just lagging a little bit behind on that direction, I would say.
What does it mean in practical terms to test computer vision ML systems? What do you need? What do people expect? Where are we right now with that process?
I think the to some extent the gold standard way of testing machine learning systems before deployment is still you have your training data, you have your validation data, and you have your test data. And you use that in various ways to train your model to find the best architecture of the model, and to then decide whether it's kind of ready to be shipped. But that's sort of a bit of a flawed approach, and I think many people realize that, because when you then deploy the model into production, I think by now most people know that things look a little bit different, and that probably what you shipped initially was not quite the right thing and maybe needs some further work and further fine-tuning. So I think what a lot of people follow is what we call like a ship to test strategy. So where you deploy it, but not with the intention of this being the real final deal, but to actually test whether it works. And I think that's good in some sense, because it lets you get out the door quickly and improve quickly. But at the end of the day, if I am a customer who is accustomed to getting software that just works on day one, that's not a fantastic experience. And I think ultimately, to provide the best customer experience and to build safe systems, we need to change the focus a little bit from this shipping to test to actually test it properly to then ship a system that's already mature and already working well. And of course, we can then iteratively improve that. But I think the strategy of testing it before we deploy, there's a lot of work that can be done on that pre-deployment first testing. And maybe Matteo can tell you a little bit more about the things we kind of have in mind there.
Yeah, absolutely. So I think there indeed needs to be a bit of a fundamental mentality shift from this, ship to test to a more test to ship mentality, which is, I guess, what's done rather in the traditional software development, and it's related to test-driven development and all these different concepts, right? And I think at the highest level, and I would be very happy if we can go in different directions here. So it's really very high level. We see testing of ML systems a bit like a three-layer system, a three-layer approach. At the highest level, you really want to test your system, and I think this is a very interesting discussion to be had, because it is our fundamental belief that a model is often not enough to have a purely safe system. So often, in critical settings like autonomous driving, you may need to reach accuracies and performances that are just orders of magnitude away from anything you would get with a single model, no matter how good the model is. So then you need to add system level tricks that are very well understood in other areas of safety engineering and so on, that help you get there. And I think at the highest level, you really have to test that system, that end-to-end system. Again, happy to dive in there a little bit more. And at that level, you may want to test not only the end-to-end performance, but things like latency. Like, is this working on device well? Like, can I actually do I have enough redundancy so that if some of the components of my system fail, I can actually still perform, and so on. Then goes the next level, which is around really model testing, and models will inevitably be a component of this system. And at that level, we think of testing in several directions. There are ultimately what you want to do is really assess generalization, and you want to assess how, like, ultimately there's always a gap between what you have to test and train and what the real world will throw at you, and there is just so much variability and like a combinatorial explosion of factors that can impact the real world that plus a moving target, right? That the real world will be always changing. And so ultimately, we need to assess performance given what we have, and try to bridge that gap as much as we can while we build the system. And for that, of course, you have the classical metrics that we all know and love. But you often have to go way beyond that. You have to test things around model robustness. So how does my model react to changes in the real world? And does it behave gracefully as you do that? Very, very importantly, how does it work on key slices of your data? So it is often, like, generalization is often thought about, or performance in terms of a probability distribution of your system, but in reality, often the tails matter a lot. Often, even if something is in the tail of the distribution and indeed very rarely observed in practice, and therefore would be kind of ignored by any aggregate metric, maybe that's precisely what you care about. And testing these kind of things is extremely important at this level. And then at the lower level, you really have the data and the data testing. And I think we very much adhere to this idea that of some kind of data-centric ML, where the work is not really in like finding the perfect architecture that by chance overfits on your data, on your test data, or something like that, but rather to work on having the right data for the problem and really understanding as quickly as possible what data you're missing and what data you need to get in multiple ways so that you actually get to that system that you want to build. And so at the data level, you really have to test several things like representativity, simple things like duplications and corruptions, but also like shortcuts, biases. There are many things that can be tested at the data level, and essentially by having good coverage at these 3 levels of testing, we believe that you can, make a massive progress towards a rather test-to-ship like strategy.
But yeah, that's a really interesting kind of 3-pronged approach, and it definitely seems of those 3 that perhaps the middle like model testing part is maybe the one where people have focused on more. At least that's my understanding of what's being done. And then nowadays you have a little bit more emphasis on the data testing side, although it's unclear how much people are actually doing this versus just saying that they're doing data-centric approaches or whatever. But I'd definitely be interested in hearing more about that top layer of kind of the end-to-end system level testing, because that, I don't know, I don't feel you hear as much about. And yeah, I'd be interested to hear your approach or your insights on what you find works with that.
Maybe maybe I start by illustrating what we mean with system, right? So there's obviously the system that at the end of the day gets shipped to the customer, right? And that, in a simplified sense, gets an image and outputs something. And part of that will normally be a model or an ensemble of models, or some other architecture you have chosen to perform your core task. But let's say your core task is detecting stop signs or something like that, and you build a model to do that. Then there are other auxiliary systems that you may want to put into that. For example, something which detects against out of distribution stop signs, and that may be a totally different model in itself. It's kind of a safeguard mechanism of saying, okay, you have this stop sign detector, but the data that I got looks nothing like I previously saw. Don't trust the output. So what I mean to say by that is that there may be various components in one system. And then you should test all of these in isolation, of course. But at the end of the day, you also need to test the aggregate of it all, right? If I feed something in which is not expected, does my stop sign detector just produce an output, or does it actually flag that is something wrong there? So there, it's really important to have a holistic view of how, what is the expected behavior, not only on the model level, but on this higher level, and how can I test for all of these behaviors?
How much of that can be automated versus needing kind of humans in the loop? Because I mean, obviously with images, like you need to do some kind of statistical calculations around distributions and things like that to be able to understand, like, there's still you're still maybe one level away from the actual representations of what's going on in the images.
So maybe what do you mean exactly by which parts can be automated?
Just in terms of what you were saying in terms of understanding like how a model is performing and where its shortcomings are, or whatever is being output from the model. How are you comparing those two things, aside from just the fact that maybe you have a validation data set or so on, which, as we mentioned earlier, like comes with
Yeah, I mean, I think one of the interesting ways of doing that is that at a system level, you certainly have expected behaviors that you can talk about, right? Maybe one expected behavior would be that very simply, if you have a stop sign and you horizontally flip the image, you may be not expecting that the output is the same, because if you flip around the center, the letters don't make any sense anymore. So that's a behavior that you can test at the system level. And you can imagine that similarly to traditional software, you can write these behaviors, encode them in tests that include some data, but also the behavior, and then check at that system level does this actually behave like I intended?
Yeah, and I would complement that with saying that I do believe that a lot of this can be automated, and should be automated for reasons that I can mention afterwards. But I think inevitably there will be a human in the loop. Like I think the way we think about this is really um, something like what we built can sit at different stages in the development process, but it is fundamentally around the development process, right? And so I think the kind of things you want to, so assuming you have some labels, for example, and even if you go beyond the system and just talk about the single model, there are there's a lot of research in the direction of fuzz testing and metamorphic relations, which, as Matthias was implying, say even if you have some labels, there are some modifications on these images that should actually preserve those labels. A rotated dog is still a dog. And so but way beyond that, you can really start to decompose how do changes in the real world occur. And in some sense you end up with significantly more labels and images to test in, right? But even if you go beyond that, I think fundamentally what you want to answer for development teams and the humans in the loop is really um, what what are the areas of highest uncertainty right now. What are perhaps the things that seem to indicate the highest risk? Where are the slices where you seem to have really problematic performance? Um, what are robustness issues that seem to really affect your model? And then as a developer or a team building such systems, you can really decide to prioritize. Like, what should I do next? And in some sense, that automation or those automatic insights around how do you poke holes into these systems and actually try to uh, look for failures and try to understand the behaviors where they break and they don't, which can all be, as Matthias said, encoded in very clear expected behaviors. Ultimately, that should lead to an action from a human in the loop. And this can go in many directions. Not only, like, you can often, what people have is they have a massive data set that is unlabeled. You collect multiple cameras, multiple frames a second, just a lot, and then you just don't know what to label. You have limited capabilities, right? And so a fundamental question then becomes, how do you get feedback from your tests and from your automated insights, so that you know what data to get next, what data to label next, how do you proceed, and ultimately, I think that's where things really help. And I think, just to not to diverge too much, but I think the idea of having a human in the loop is almost necessary in many instances. And as Matthias was saying, like, a key component of testing is partially that once you deploy, you have a very good notion of what you use to build your system. So you're in a very good position to identify problematic inputs on the fly. And I think kind of graceful failure, in some sense, like that you're able to not just silently fail, but just collapse to a situation where a human can perhaps take over. That's really an ideal situation to be in. The kind of silent failures that ML systems suffer from are probably one of the largest challenges to tackle in this whole story.
Maybe that's a good place if one of you could describe a little bit what exactly you build at Lakera, because I guess you're working directly to address some of these issues.
So I think we, as Matthias mentioned at the beginning, we're quite obsessed with the very high level question of building systems that we can trust and that are safe. And we start with computer vision, and right now we really build in two directions. Like, one is really, it's a product called ML Test, and the core value proposition of ML Test is really to essentially open up your black box and tell you where your system fails, and try to quantify the risk that this presents for failures in operation. So essentially, it's a tool for assessing how your system will actually perform, and more precisely, where it is likely to fail. I think, as we were saying earlier, the the main difference between traditional software and ML is that the complexity emerges at day one. You build your startup, you train your first system, and then you have a complex system right there. And now what we have learned from speaking to many hundreds of people building applications in all sorts of areas of ML and computer vision is that the issue of then building the infrastructure and the testing around that system often absorbs a lot of the resources of these teams, often small teams. The result of that is that often only the big players can innovate because only they can invest in this kind of infrastructure. And the issue with that is that not only does it take a lot of resources to build a testing infrastructure, but because of the shortcomings in the maybe research and know-how direction, it's a hard question to answer. What does it even mean to test a machine learning system? And in that sense, what we do is that, as opposed to traditional systems, I think the ML world will really go in a direction where a lot of this testing is automated because that know-how really requires a lot of expertise and time and development. And ML test is really a product that tries to equip all computer vision teams out there with a Tesla level, testing infrastructure without having to build it in-house. And as I mentioned, it does so by finding vulnerabilities in these machine learning systems that go in several directions. They go in the data direction, in the robustness direction, automatic finding of failure buckets. Where does your system fail based on image properties, based on metadata, and how can you use that to prioritize your development and to know, what you should do next, finally. In addition to that, it also brings a transparency and communication angle. As Matthias was mentioning, often one of the hard questions to answer is, does our system work in these situations? Or, where does our system, and more importantly, even, where does our system not work? I think these are questions that are very difficult to answer, and that we work really hard to answer for people. And I'll let Matthias add anything he may be missing on the ML test side, but we also think a lot about the operational side as well. So what happens once you're in production, and having used ML test to build your system, we're in a very good position to understand what is unusual for that system and what is really outside of the operational design domain, so to say, of that the system was trained on. And we're focusing quite a lot there on actually trying to alert failures early, because undeniably the world will change, data will change, and often the kind of failures that will appear will take a very long time to be identified, and we want to focus on those issues.
One of the things that we work very hard on the ML test side is that with all this testing, not only should you get a very good idea where your model fails, but also exactly under which conditions it works. And then that's sort of the base assumption that you can then work on by deploying it. And then ML Guard, what it does is also then allow you to assess, am I still sort of in that range of base performance, or have I now degraded, and should I maybe, alert the user or retrain my models?
I guess you work with different industries. I know there's certainly a lot of focus on your website about medical use cases, but I know you work with other industries. I'm curious, have you found that there are different processes or expectations around how people develop and deploy their models? I don't know. I'm just thinking of certain industries where there may be some certain privacy boundaries or things which need to be in a certain way, which dictates what you can and can't do in terms of how you're testing things.
Yes, I think there's definitely differences, particularly on the angle you just mentioned, which is data privacy. So in the medical imaging domain, but also partially in robotics, you can't really expect that your application sends you back all the data that it finds during operation. Right? Customarily, you do not get access to the data when the system is deployed. And that makes these challenges all the more harder, because how are you going to know whether your system is underperforming if you've never seen the data, and if you could never label the data? So that is definitely an aspect that varies. I don't know if it's so much from industry to industry or from application to application, but certainly, data privacy is a very big topic in the healthcare sector. That's
Yeah,
for
and I
sure. Yeah.
think just to add to that, I think something else that is very interesting is that in addition to the kind of core testing functionalities that people building RGB computer vision may need, and that's why we really try to address with our products. I think there is a fundamental component that is kind of behind that also, which is certification. So many of the companies we work with in healthcare, but also in other areas, have actually do have to go through certification processes, and these certification processes are evolving. Right now I think there's a general line of work that is really trying to understand what it even means to certify these ML systems. But I think that's clearly also like something that is varies a little bit depending on the different use cases, which are what kind of evidence do we need to provide for certification, and ultimately that is something, that's another angle that provides a little bit of variability in what people care most about. There is kind of the does it does where does my system not work, and then in addition there is kind of the requirement side for certification, which of course needs to fit in the picture.
Curious how you see the role of annotation into this whole process. It seems like certain companies seem to really give it a lot of priority and value, and others it's almost an afterthought. How is this part of the overall cycle?
I think annotation is quite key. As we were saying, we fundamentally believe that probably one of the core insight as part of your development that you may get from testing, and of course it's not necessarily the same, depends on where the testing sits in the pipeline. Of course there is testing during development, there is testing before sending to production. All of this fulfills different role, but at least the testing that is done during training, I believe, ultimately should lead to the question of what data do I gather next, and what do I annotate next. And I think therefore annotation plays a crucial role. Something we find, for example, is that often companies ask very, very late, what are the key metadata dimensions, for example, that we need to keep track on our data so that we can do good testing. Of course, we care a lot at Lakera of testing from image features alone, and we do a lot of work on that direction. But if you already know the age of the patient, the gender of the patient, the demographic, the hospital he was taking on, the machine he was taking on, for example, you're in a much better position to understand what are concerning areas, where the model is not performing. And in that direction, I believe the question of even defining the annotation task, it's much better to ask these questions early. And then and maybe that's the earliest impact that test-driven development can have in ML, which is it forces you to ask beforehand, what are the things that I need to collect, what are the things that I need to annotate. But I think there is a clear loop in that sense between testing insights during development and then data quality, data annotation, and in that sense, I believe that these play a very key role. And if you're working with poorly annotated data that perhaps does not even fit quite the right granularity for the problem you're trying to solve, that is missing the metadata that you need, etc., you're putting yourself in a much worse position to actually get your system to production.
And maybe I add on to that, that what Mateo just raised, the point of metadata, that is actually something which is differently developed in different industries, I would say. And that is primarily driven by the necessity of the problems that people in these industries solve. Like if you build a medical imaging device and you want to get this through FDA certification, they will ask you questions like, well, does this system work equally well on patients of the age 25 or 50? Now, if all you have is an image and a label whether this image was cancerous or not, there's no way that you can answer that question. So that's why companies in the medical imaging space, for example, place more emphasis on collecting this metadata early, because they know they will have to answer these types of questions, which ultimately tell you a lot about where your system works and where it doesn't work. And another good example would be autonomous driving. Actually, they have, by nature of the data that they collect, they have a lot of metadata that are not quite, maybe necessary to do the core task, but that help them a lot in understanding where does the system work, where do they need more data, and where do they need to focus their resources on. So in that sense, the more of this auxiliary data you have, I think the faster you can ultimately develop and the better system you can build, because it creates transparency.
I kind of see the role that synthetic data plays. It's somehow a part of the annotation story as well. Like how significant is that? Is this still like a developing field? So maybe we don't know fully what this is going to bring, or what the possibilities are there.
Yeah, I think it's definitely fits in there, and I think it's an important piece of the puzzle. Now, how developed it is, I think depends kind of on the application. If you look at making very high quality outdoor scenes, it's a lot of effort. But if you work on like lower fidelity data, there's maybe a lot more that you can do realistically already. But ultimately, simulation is the ideal way of testing for specific behaviors and generating these metadata at scale. Right? Not everyone is in the lucky position that autonomous driving is in, that they have more data than they can actually process. Like particularly in medical imaging, data is scarce.
And actually that leads to an interesting thought experiment, which comes back to your annotation question, which is, if you had the perfect simulator, how would you actually prioritize, which data do you ask from it so that you can indeed build a better system? Like, how do you ask the questions? How do you actually use that oracle in some sense, to even build your system? Because, even then you cannot say generate infinite data, so even then you actually have to guide that process in a way that leads you to a system that works. And so the realism of it is one angle, and as Matthias said, I think that it will and does play a key role in building good systems. But then again, it also shows you how you need some kind of guiding light in the process of building, which we believe is fundamentally test driven, to even know what questions to ask and how to play with that oracle simulator in some sense.
And I guess even at a more fundamental level, if you want to build realistic images, you have to understand all of the different ways that your images can exist in the world, what's realistic, what's not. Like it's all comes back to you understanding your data and what kinds of things are possible, I guess.
Absolutely.
Exactly. But also much like testing, I think creating high quality synthetic data is a highly specialized skill. So I don't know if I would recommend a small startup to spend vast resources on building a simulator in-house. But there are great companies who have a lot of expertise in making ultra realistic scenes.
In everything that you've been talking about, are there tools that you love working with at Lakera, things which you found really help with the whole spectrum of things that you've been talking about today?
Good question. I mean, on the ML side of tools, I think I definitely like DVC quite a bit, because it gives you nice traceability of data changes and model changes. As a developer, I use Git a lot, obviously, but that's really, I think, a key tool to establish traceability, in an ML workflow, I would say.
And you found that scales well and can handle the kinds of volumes, particularly for image data?
That's a good question. I haven't hit the wall in that sense yet.
Right.
Let me put it that way.
Okay. Yeah, no, I'm just curious to often ask people who are working in specific domains, what are the things that really excite them? And sometimes there are little tools here or there. A few weeks ago, you both, I think you were both there, maybe at a little kind of demonstration you gave of 51 by Voxel, which is, I find it a really nice way to deal with anomaly detection and so on, and nice interface and so on that many people don't know.
Yeah, absolutely. Vox 51 was really interesting. We haven't used it actively as part of our own development, but I absolutely see how such tools can make a massive difference. And then again, as you mentioned, I believe in that conversation, kind of the integration with the whole data annotation pipeline and so on is pretty essential to the value of the tool as well.
Yeah, that's maybe one of the things that at least to me, is very important, that whichever tool you use, it fits seamlessly into your workflow, and I don't have to think about it, right? And it helps me set up a professional development workflow, which is something I find on traditional software Git does so well.
Yeah, I mean that's the dream for MLOps. I'm not sure whether we're quite there yet. Just the large number of tools that you inevitably have to end up using at various stages of the pipeline. But yeah.
Yeah, I fully agree, which makes the integration aspect all the more important, that they somehow fit well together. And I think that's something for the tool developers in the MLOps community to really try take on board and push for. That if you look at one part of the process, make sure it fits in with other parts of the process, because ultimately, at a success in a development team, you go through that process a lot. So any type of friction will eventually, harm the usage and all the good intentions.
So we like to usually end the podcast with a couple of kind of quick questions. I guess Matthias, you answered the second one already somehow. So maybe I can at least we'll start with the first one. So what would be kind of a quick win that someone could add to make their putting models in production more robust, based on your experience?
Something very interesting that we found that is maybe a very easy win, I believe, and I, actually is very good to illustrate some of what's lacking in the mentality of how we develop ML systems, is that augmentations, for example, for building more robust systems are a key part of anyone's pipeline. Anyone will tell you, of course, I add brightness, I add motion blur, I add this, I add that. But then somehow there is a bit of a leap of faith. There is a leap of faith that those augmentations have the desired effect, and that actually, if you added all these brightness transformations, then your system is actually going to be robust to that. And very interestingly, so we've been playing quite a lot with state-of-the-art YOLO models, on Coco and on different data sets, and not only are these models really non-robust to a bunch of real-world variations, but even to the simple things that they were trained on, they often are not robust. They break quite badly with all of these different things. And to me, kind of a key learning there, and it says a lot about testing, is that this leap of faith is really not warranted. And in general, if you expect some of these behaviors from any work you do on the augmentation side, for example, the effect that you expect from those should be explicitly tested. And this is something that I believe can add a lot of quick wins because we find that systems are kind of non-robust at scale in many different ways, and in that sense, just something as simple as that can actually help quite significantly in getting more robust models out there.
And I guess to return to the tooling question, just to throw it out there again, like explicitly, like is there something that you feel is really missing or going kind of not being paid attention to in the space?
I think the integration question, to be honest, is pretty much key. So I think that's something that we have heard from many people, many customers, many users, and many people out there, is that they care less even fundamentally about fancy features than they care about how it integrates into their workflow. I agree with you that there's a bit of a stitching to do between all the different MLOps players, and that will take time. And I think, as things evolve, I think there'll be more clarity there. But, people use Git, like GitLab or GitHub. People use CI/CD. People use DVC. People use other forms of version control. And ultimately, if you want to do something like testing for behaviors, I think the last thing you want to do is, spin off a notebook and run some cells by changing some paths manually to make sure that you are on the right model. And I think people often, I would say, overinvest in the features at the kind of cost of not thinking too much about integration. And to me, whatever will make it out there as part of that final, more stable ecosystem will necessarily integrate very well. And I believe that's something that the field can really benefit from.
Yeah, I guess each test failure is like a future saving of some catastrophic thing which gets released into the world that you don't want to happen.
Yeah. Exactly.
Well, thank you very much for coming on. It was definitely fascinating to learn about your approach to this, and seems like a wise way to go about things that you're proposing.
Thank you so much for having us.
Thank you for listening to this latest episode of Pipeline Conversations. If you enjoyed what you heard, please consider giving us a review wherever you get your podcasts. It helps us get seen by more people, and of course, it's always nice to receive feedback. If you have suggestions for future guests, please send them over to podcast@zenml.io. Thanks. Until next time.